Great. Okay. Hello, everybody. I go by Paul, and today I'll be using David's slides to tell you about some of the hydrogen work that we've been doing. So I have been involved in most of these projects, so you could ask me questions. I hope I can answer them, but I apologize in advance. I cannot give the talk to the same depth as David would have been able to. But let's see. So, whoops, sorry. So why do we care about dense hydrogen? There are actually quite a few reasons. From the application point of view, it's very important for astrophysics. If you want to study hydrogen being the most abundant resource in the universe, it's very much related to the structure of Jupiter and Saturn. And it's also important for energy applications, for example, for inertial confinement fusion, for example, related to experiments being done at Livermore in the National Ignition Facility. And it's also one of the simplest elements on the periodic table. So in that sense, it's a great place to benchmark methods. There's no pseudopotential, and there's actually strong quantum effects because hydrogen is so light. So there are actually quite a few things that's difficult for the methods to treat, and we have experiments to compare to. So not only does it have great application, it's also a great benchmark for theoretical methods. Some of the interesting things, there are actually quite a lot of fundamental physics questions that are not fully answered in dense hydrogen, and that's another reason to be interested in it. So here's a list of quite a few things. I will introduce the liquid-liquid transition from the molecular to atomic side, but that's not the focus here. There is also an associated insulator to metal transition, and there are questions about whether they occur at the same time. Is it a first order transition and things like that. And we're also interested in what kind of crystal structures are in dense hydrogen when you really compress it, because experiments are done in these tiny diamond anvil cells, and it's extremely difficult to make X-ray measurements without breaking the diamond. There are other questions as you go to even higher pressure. Could hydrogen be a very low temperature quantum liquid? What are the actual properties? And could there be superconducting, superfluid phases, and lots of other interesting questions to be answered? Now, of course, we want to answer these type of questions from a simulation perspective. And the method that David and coworkers have developed, called the coupled electron ion Monte Carlo method, has been extremely valuable in the space of dense hydrogen. So the method just goes, you use diffusion Monte Carlo to simulate electrons at 0 temperature, and you couple it to path integral simulation of the proton at finite temperature. That way, you're able to cover the temperature and pressure phase diagram of dense hydrogen and make reliable predictions. So on this plot, I'm showing this stuff related to liquid-liquid transition. That is, at low density, at low pressure, you have this molecular liquid. The hydrogen molecules form bonds, and as you compress it, eventually there will be a bond breaking transition, and you form a metallic fluid. And in the green here are these coupled electron ion coupled electron ion predictions for the conditions of the liquid-liquid transition as a first order transition, predicted for deuterium. And these calculations were first performed in 2010. That was quite a while ago. It was later, and then the experiments came much later in 2015. So the first experiment is dynamic compression experiment from Sandia at the Z machine. The time scale was extremely quick. And then later on, there's this recent work, this recent work from the Livermore group, where they did the dynamic compression at a much longer time scale, allowing the system to equilibrate a little bit better. And they found that their results are in very good agreement with the coupled electron ion. Another thing to note is that there are DFT lines on here. So this orange dashed line is the prediction from PPE. It predicts the dissociation transition way too early. And this blue solid line is from van der Waals DF2. It predicts the transition too late. And finally, this dashed line is from van der Waals DF1. It predicts the transition at a reasonable place. And actually, our very own Ray Clay has benchmarked van der Waals DF1 against quantum Monte Carlo and found that it gives very good forces. So it's actually not too much a surprise that it agrees with QMC, but the match is quite satisfactory. So this method has been used successfully for quite a few properties. I should also mention there have been recent calculations optical and band gap properties of hydrogen performed by Vitali. I'm not sure he's here. But the CP requirements for the couple electron ion method is quite extreme, so it's difficult to do a lot of science. So we want to be able to use this kind of accuracy and do larger systems and explore longer timescales. One particularly interesting thing that they have found during the study of dense hydrogen with couple electron ion is that there's some hint that the system wants to localize at extremely high temperatures, such as around 1500 Kelvin. And that's way above what people have expected from experiment. So we would like to investigate if that's real. So in order to do that, we just computed a bunch of quantum Monte Carlo forces, create a machine learning force field, and then use that force field to explore the melting transition of molecular hydrogen. The experiment on molecular hydrogen melting was this 2017 experiment in diamond anvil cell, and they just measure the Raman spectrum and see when the peaks in the Raman spectrum disappears. Now, this is kind of a controversial signal because the signal could disappear due to other things like sample leaking out or problems with the apparatus. So it's kind of an indirect observation, and there hasn't been another experiment after this. And the only theoretical comparisons, these various color lines, all use the PBE functional. And we've seen in the liquid-liquid transition case, PBE has a large error compared to QMC. So we would like to use QMC accuracy and redo this melting study. So the first step of this study was to create a database of quantum Monte Carlo forces. And we ran a whole lot of molecular dynamics simulation using ab initio, DFT, as well as other methods, generated 100,000 configurations, performed DFT on them, and selected 20,000 of them to run quantum Monte Carlo. So this work would totally be impossible without QMCPACK, which is extremely efficient, and the implementation of the Chiesa force estimator within it. And the Chiesa force estimator is basically you represent the force inside a radius of the atom by an approximate form that screens out the divergence at 1 over r as r goes to 0, and the rest of it is just a sum over 1 over r when you're outside of this radius. Details in this paper, and it's implemented in QMCPACK, and we were able to use it to generate a lot of data for this project. And then once this data is available, we train a machine learning force field on it. And the machine learning framework was developed by the Princeton group called DeepMD. Now, we didn't directly fit the QMC energy and forces to DeepMD for 2 reasons. One is that we wanted to impose a physical constraint when the protons get too close. We want them to repel each other. We want this to be built in. This not only ensures that in your simulation, things don't just clump up together, because if machine learning haven't seen these configurations, it could predict the low energy and your simulation will just have a clump. So this enforces the physical constraint and allows us to not sample configurations where the electrons are very close. So we don't need that training data. The second thing we did was that we trained a model for with DFT forces, and then the final model is only the difference between QMC and the DFT and the pair potential forces. And this allowed the final model to be rather smooth, and the values are small, so we don't need as many data points to train it. So once we have the force field, we ran path integral Monte Carlo simulation using this force field as the Born-Oppenheimer surface of the electrons to recalculate the phase diagram of solid molecular hydrogen. We can recover the HCP phase at low pressure and low density. Then we found a new solid phase with FFMM symmetry. Basically, it looks like this in the red square. What happens is that the 2 layers in HCP shift so that the molecule on the top layer is now on the edge of the triangle rather than at the center of the triangle. And that's the new phase. And the triangle also slightly distorts. Some important things to note is that the protons are extremely quantum in dense hydrogen. So on the right, we're showing the azimuthal angle, that's the theta of the hydrogen molecule relative to the z-axis, and that's the polar angle. And then on the right is the azimuthal angle of the hydrogen in plane. You can see that at high temperature, they are both flat, meaning the hydrogen molecule is spherical isotropic. Whereas if you lower the temperature, then the molecule like to lie in plane. And in the various solid phases, it either has one preferred direction or three preferred direction in the C2C structure. And not only does it have this different direction preference, it has large libration motion around it. So the quantum effect, the quantum effect of the protons is important to take into account. So here is the melting lines from our calculations. So we fit three models, one directly to PBE, one directly to van der Waals DF1, and finally one with the three-layer that we've shown before. So the PBE one, so the solid lines are quantum results. The open circles are classical. So the PBE line is the lowest and it agrees with previous PBE calculations. And you can see as you increase the accuracy of the electronic structure method, the melting line goes up, and eventually you see solid around 1500 Kelvin. On the bottom, we also show that our equation of state data agrees fairly well with a recent X-ray experiment that we're able to go up to this pressure. Kevin, who's in the audience, has done work, also extended this melting line to the atomic phase. And he found actually two very interesting things. First is that the quantum effect in the atomic phase is extremely important for the melting temperature. So on the top line, the blue line is the melting line of classical protons as a function of pressure. And the green line is deuterium, and the red line is for hydrogen. You can see the slope eventually goes down. And when you're in hydrogen, it shows that the density of the liquid is actually higher than the density of the solid. Another thing Kevin discovered is that in liquid hydrogen, there's a very anomalous double peak structure in the structure factor for the proton. Usually for the liquid, it should be a smooth curve with one single bump at the radius of the atom, essentially. But there's an extra bump that changes with pressure, roughly following 2 kF. And this could produce some interesting metallic behavior that will have ramification in the experiment, but the details are still being worked out. So we think quantum Monte Carlo can make a large impact in the field of in modeling materials in conjunction with this machine learned interatomic potential. We're able to provide data that has higher accuracy than DFT. We're able to model exotic phases like superconductivity, like a superconductor, and we don't have basis errors. Basically, we always work in a continuum basis limit rather than the quantum chemistry methods such as coupled cluster, which is accurate but would have a large phase effect. But in order for QMC to make good contributions, we need to be able to understand how the noise affects the training and in the forces. So one more advantage of quantum Monte Carlo is that extra averaging is basically free. And by extra averagings, we mean things like twist averaging that you need for a metallic phase, path integral averaging for the protons, and sampling different atomic configurations when you train a machine learning potential. So I think we have a large advantage, and by using large computers, we have a big advantage in simulating extended system with periodic bunch conditions and in complex systems with many different atoms together. So before I wrap up, I just want to point out in the recent archive posting, we analyzed the energies and noises in the models that we fit for this project, and found interesting ways to estimate the error to the exact solution by using the errors that you can measure. That is the statistical error and the model error. On the left, I'm showing the energy error. And you can see that the energy error from DFT to QMC is around 2 EV, whereas the energy error of the machine learning model is 1 EV, so much closer to the right answer. And for the forces, the DFT will be 530, whereas for QMC, it's only less than 300. Okay. So finally, here's our COVID team that worked on these projects. Kevin and Shupan are in the audience. Scott has worked a lot on all of these machine learning work. And Ricky actually did a lot of the melting calculations. And Marcus and Carlo, who are, you guys probably know. So that's it. And I will leave up David's challenges and opportunities for us and take any questions.
Thanks very much for the presentation, particularly with not your slide deck. Open for questions in the room or online. So I have a question, but this may be answered in the archive paper, but were you able to see any particular pattern in the errors from the forces from the QMC data and the DFT data? So particular structures, for example, that were prone to error.
Yeah, well, so that's a really interesting question. I don't have a great answer for it, but one thing I will say is that we notice that PBE force error go in different directions compared to a QMC. But I think Ray knows this because PBE underbinds, it wants the molecules to be long, and van der Waals overbinds, it wants the molecules to be very short, whereas QMC finds you a middle ground. So that's the kind of one of the observations we make. But yeah, I don't have more detailed answers to that.
Thanks so much. Last call for questions. All right, let's thank Paul once more time.
Thanks.